Hi, my name is James Walker, and I'm going to talk to you about my work using electrostatic torques to manage angular momentum with uncontrolled rotating targets. When exposed to the energetic plasma environment, conducting spacecraft will actually charge. So electrons, ions, and photons will impact the conducting surface, generating currents and causing that spacecraft to charge. Once these currents reach an equilibrium, the spacecraft will maintain a consistent floating potential. Um, in this work, which is mainly applicable to geostationary regions and higher altitude orbits, spacecraft potentials can reach thousands to 10,000s of volts, so you can get very significant electrostatic potentials. And some effects that arise are first surface charging, where it's the surface of the spacecraft that acquires this potential, which generates an electric field which interacts with the surrounding plasma. You can also get differential charging, where if the spacecraft isn't fully conducting, if there are components that are electrically isolated, they can charge to different potentials, which then leads to different aspects such as arcing between the two components. The interaction that is most explored by us at the University of Colorado Boulder is electrostatic interactions between two charged spacecraft. So two objects charged in close proximity are going to exert electrostatic forces and torques on one another. And why these are really interesting is it gives a spacecraft the ability to contactlessly manipulate the relative motion of a target object. And we've been looking at how these interactions can be used to advance proximity operations. So one technique that's been looked at is cool information flying. The idea is to maintain the formation of charged satellites purely through these electrostatic forces to reduce on fuel costs. Another technique is electrostatic detumbling, where you have a uncontrolled tumbling debris object. You approach with a servicing spacecraft. By controlling the potential on both the debris and the controlled spacecraft, you can actually apply a torque that spins down the rotating debris. Once it's spun down, you can then dock to it or perform debris removal as necessary. One technique that's been thoroughly explored in our lab is the electrostatic tractor. Now, the idea is to charge a debris object positive while you yourself charges negative. The opposing charges creates an attractive force that then allows the servicer to tug the debris object. Now, this is for geostationary debris, so it tugs the debris object to a graveyard orbit where it's no longer going to interact with those high-value geosatellites. Now, one aspect that arises with these charged maneuvers is that in order to generate significant forces and torques, you have to have highly charged spacecraft with small separation distances to generate these significant forces. But you're also going to generate these significant torques. So these spacecraft need a way to manage the buildup of angular momentum during these electrostatic maneuvers. For the scenario that we're going to explore in this paper, we have a plus 10 kV charged target and a negative 10 kV charged target and a positive 10 kV charged servicer over a 30-meter separation distance. Now, this configuration can generate torques on the millinewton level, which can be a big concern because if we propagate this scenario for 30 hours, the reaction wheel speed will have to increase up to 6,000 RPM to store this angular momentum, which is the saturation limit for many of the large reaction wheels out there. So this is a concern that over a little over a day, reaction wheels will saturate. So we're going to have to perform daily desat maneuvers in order to maintain our attitude control. Now, chemical thrusters are a common method for maintaining angular momentum to burn these thrusters and apply that external torque. However, chemical thrusters are limited by the propellant that's carried, as well as because you're emitting matter, this can actually contaminate spacecraft surfaces, which changes its charging behavior, which can be a concern during these electrostatic maneuvers. So instead, we actually look at a different method. We look at using the electrostatic torques generated between two spacecraft to manage the momentum, electrostatic momentum management. And the key behind this idea is that the electrostatic torque that's generated between two spacecraft is attitude dependent. So it's dependent on the relative attitude of the two objects. So by rotating the servicer, we can actually generate different torques on the servicing spacecraft. And this figure here shows for a stationary target all the different torques that the servicer can experience by manipulating its attitude. So the idea is that you maintain your first attitude, you're performing your science, you're tugging, and as you maintain it, your reaction will spin up to account for the electrostatic torque. Once you reach your DSAT threshold, you rotate to a second attitude where the generated torque acts opposite your stored angular momentum vector, which then allows you to spin down your reaction wheels. Once they're spun down, you rotate back to your original attitude. In order to do this analysis, we have to compute the force and torque between the two spacecraft, and we do this using the multi-sphere method. The idea is to discretize the two spacecraft as a collection of spheres. This makes it quicker to compute the charge on each of the objects. And then once you have the charge of each sphere, you calculate the force generated between each of them. The net force on each collection of spheres will be the net force and torque acting on both targets, both spacecraft. And this allows for much quicker analysis used for faster than real-time attitude dynamics modeling. So the first thing that is done is a database of all the possible torques that the servicer experiences is computed. So for a stationary target, the servicer is rotated to every potential attitude and the torque computed. Now with this database, it only has to be computed once before the maneuver is performed. And then once the DSAT threshold of the reaction wheels is reached, this database is then searched to find the electrostatic torque and then the associated attitude that acts most opposite the stored angular momentum vector. We do this by taking the normalized dot product between the two vectors and finding the minimum value. So the value that's going to be closest to -1. And then this is how we identify our second attitude. Now, prior work that has been looking at developing electrostatic momentum management, it's been about building this database and then using it considering a stationary target. Now, that's unrealistic because as the servicer experiences the electrostatic torque, it's going to generate a reciprocal torque on the target, causing it to rotate. And these rotations can be a concern because when we built this database, we assumed a stationary object. So as the target rotates, the torque that the servicer is going to experience is not the one predicted by the database. And that will lead to a buildup of angular momentum because we're experiencing a torque that isn't actually opposite our angular momentum vector. And we want to look at how this buildup in angular momentum affects our ability to actually perform these maneuvers. Well, what we found is, at least for the configuration here, it doesn't seem to be a major concern. Running 100-hour simulation, we get 3 different momentum management maneuvers, and each time we're able to keep the reaction wheel speed below that 6,000 reaction wheel speed threshold. And we're also able to bring our angular momentum down to near zero. It doesn't reach zero because we still get buildup due to the inconsistent torques and torques that we see during the slew itself. But by rotating between these two attitudes, we're able to have this nice bounded angular momentum behavior. Now, expanding this to longer simulation times, we run it for 1,000 hours, and we see, again, similar behavior. We keep the reaction wheel speed bounded, and over the 1,000 hours, we perform 27 desaturation maneuvers to get rid of a total of a little over 1,600 Newton-meter seconds of angular momentum. But you do see that there is a general increase in the angular momentum. After about 500 to 600 hours, you can see a bit more steadily increase where we're not able to fully dump the momentum of the servicer onto the target. We end up retaining some, and it continues to build as the simulation continues. And it ends up being, after 1,000 hours, about 13 Newton-meter seconds of angular momentum. And this momentum is actually around the X and Y axes. So this maneuver primarily dumps around the Z axis, so we do get buildup in the other axes. And this could be a concern because it suggests that maybe we can't fully control the angular momentum of the servicer using only these electrostatic torques. And we can take a look at this further by looking at the torques generated around these principal axes, around just the X, Y, and Z axes. So the previous scenario showed how we're able to manage it around the Z axes. So Z axis momentum isn't a major concern. And we see a similar behavior around the y-axis. So looking at just our ability to dump a pure angular momentum around the y-axis, we're able to fully bring the angular momentum down to near zero. It still doesn't reach fully zero because we still get that buildup in the x and now z axes, but we're able to dump our reaction wheel speed and bring it down to a near zero value. So buildup in the y-axis and z-axis aren't a major concern because we're able to dump this momentum if needed. Around the x-axis, this isn't the case. So in fact, if we start with an angular momentum purely around the x-axis, we get that the normalized dot product between the two has a minimum of negative 0.14. So for the torque that has the largest x-axis component, still is relatively perpendicular to our angular momentum vector. Now, this is a concern because it leads to momentum buildup if this is chosen as our second attitude. And we actually see that in the simulation that we run, is that during the slew, the torques that the surfacer experiences actually brings this dot product between, after the slew, the angular momentum vector and the electrostatic momentum vector to be greater than zero. So it actually acts in the same direction, and we increase our angular momentum by doing these maneuvers. So pure x-axis momentum can't properly manage using only the electrostatic torques. Now, this tells us that electrostatic momentum management can't guarantee that we can fully control the momentum of the servicer, and that additional momentum management strategies may still be needed to fully remove angular momentum from the servicer. But by implementing EMM, we have actually been able to significantly reduce the dependence on, say, chemical thrusters, because instead of having 27 burns to dump 1,600 newton meter seconds of angular momentum, we only have to perform one burn after 1,000 hours to dump 13 newton meter seconds. So still, we get the significantly reduced dependence on the fuel. The other aspect that we look at is the servicer torques. So because we have this rotating target, it's a little surprising we get this very nice bounded behavior in the momentum. We still do get buildup, but at least for that first 500 hours, we're able to almost bring the momentum down to zero. Now, this is surprising because as the target rotates, the torque we experience changes. So we investigate this by actually taking the first and second attitudes that the servicer rotates between and looking at all the torques generated for any servicer attitude. So we rotate the servicer like we rotate the target like we did before with the servicer, so that the servicer's attitude remains constant. Now the target is rotating. And looking at all the torques generated on the servicer, we get that each of them has a very dominant z-axis component. There are still x and y components, but they're all primarily in the z-axis. And this is why we get that nice bounded behavior, because even though we are building up some momentum around the y and the x, we're still mainly bringing it about the z-axis. So we still are able to dump the significant portion of our angular momentum. Well, that's not actually true for all attitudes. We have a relatively nice attitude here. If we take a look at, say, the solar panel pointed towards or away from the servicer, we get a much wider torque distribution. You can see here that we can actually get torques around the positive z and y axes for the same servicer attitude. Now, this is a concern because that means that as the target rotates, the servicer can experience torque in any direction. So it's unlikely to be about the negative of the angular momentum vector. And so we won't properly be able to dump our momentum. And taking this analysis, what we realize is that these inconsistent torques are generated when the servicer has a relatively strong symmetry in the attitude relative to the target. So you can see here, we get these relatively symmetrical views from the target, and that's what leads to these inconsistent torques. And we can take a look at that further by looking at the charge concentrations on each of the spacecraft. So as the spacecraft charges, it's actually going to lead to higher charges along the thinner exterior regions of the spacecraft, so such as these solar panels. So it's the location of these solar panels that really drive the torque generation. And so if we have the solar panel pointed at the target, just rotating 45 degrees about that z-axis, you can see that we can apply torques in the plus or minus z-axis direction. We can get these torques acting in completely opposite directions for the same servicer attitude. We don't see that when we look at an asymmetric target. And that's because these charge concentrations are far away from the surfacer. So we have these high charge concentrations at a distance away from the surfacer center of mass. You're going to get these large torques. Now, these large torques are always going to be pointed in a negative z direction because that surfacer is going to attract the target's going to attract the solar panel to it, regardless of its orientation. And the big takeaway here, and one of the big takeaways from the paper in general, is that the surfacer attitudes need to be asymmetric relative to our surfacer in order to get our consistent torques. And our consistent torques are necessary for our angular momentum management. The beauty of that is that we control the shape of our surfacer and we control the initial attitude that we want to maintain. So we can develop it such that the surfacer maintains a strong asymmetry so we can actually perform these momentum management maneuvers. Now, there is more work to look into. Specifically, we want to quantify the torque distribution so we can identify attitudes that have these inconsistent torques. So then we can remove them as potential attitudes as the anti-parallel torque attitude, because that will allow us to have all the attitudes that the surfacer achieves will be these consistent torque attitudes. Another thing we want to look at is how uncertainty in the target's geometry affects our ability to build and use this database because we are working with debris objects. It is unlikely we're going to know the shape of the object extremely well. And then finally, we want to look at different surfacer and target configurations. So we've only looked at an asymmetric surfacer and asymmetric target. What happens if we have a symmetric target and an asymmetric? What happens if we have a symmetric surfacer and an asymmetric target? How does that affect our ability to generate these consistent torque attitudes, and how does that limit our ability to perform electrostatic momentum management? This work has been funded by the NDSIC Fellowship, as well as a lot of the work that has gone into the electrostatic factor has been funded through the office of the AFOSR. So thank everyone for their time and watching this. If you have any questions, feel free to reach out. I'd be happy to answer them.